This is section 4-3, the second derivative test. So let's start by talking about concavity, okay? If you think back to when we talked about parabolas, we said that when we were graphing them that they'd either be concave up or concave down, all right? Well, here's a fairly complex graph, and let's look at what we've got here. And if we look at this portion here is concave down, okay? Its opening is down, all right? Now, if we look at this portion here is concave up. Granted, we've only got a small portion of it, but you can see that it's concave up. Now, if I move on to the right, we got another section here, which is concave down, all right? Again, the opening is down, so it's concave down. And then lastly, we've got this last section here, which is concave up. So this is what we mean by concavity, all right? Now you may have noticed 3 points here, 3 red points on the graph. And these are referred to as points of inflection, all right? Points of inflection. Well, what do you mean by points of inflection? This is where the function changes concavity. So if we look at this first part here, we've got concave down, but then at this point here, we change to be concave up. All right? And similarly, at this point, we change to be concave down, and then at this point, we change to be concave up. Okay, these are what are referred to as points of inflection, where the function changes concavity. Now, another way of looking at these points of inflection, it's where the second derivative is equal to 0 or is undefined, okay? So if we were to take, this is the original function. If we took the first derivative and then the second derivative, we would find that at these points here, all right, these 3 red points, which are the points of inflection, this is where the second derivative is 0 or undefined. In this case, I believe they're all going to be 0 here. Well, if the second derivative is 0 at these points of inflection, what is it on either side of these points of inflection? Well, what we're going to find is when it's concave down, all right, the second derivative is going to be less than 0 or negative. When it's concave up, the second derivative is going to be greater than 0 or positive, all right? And similarly, we can see for these other two, whenever it's concave down, the second derivative is negative. Whenever it's concave up, the second derivative is positive. So how could we define the second derivative test? Well, suppose we have a function where the first derivative at a is equal to 0, okay? So therefore, a is a critical point, all right? If the second derivative at that critical point is greater than 0, or in other words, if that second derivative at that critical point is positive, then the function has a relative minimum at that critical point. That is considered to be a relative minimum. And if you think about that, if the second derivative is positive, that means we're concave up, so therefore it's a minimum. Similarly, if the second derivative is less than 0 or negative, then we have a relative maximum. And again, remember that if the second derivative is negative, all right, we're concave down, and that means we have a maximum at that point. Well, let's look at an example here to see if we can explain this further of the second derivative test. So use the second derivative test to find the relative extrema for f of x is equal to x to the fourth minus 2x squared. Well, the first thing we're going to do is find the critical points by taking the first derivative, okay? So if I take the first derivative of this function, we come out with 4x to the third minus 4x, all right? Factor that out and solve for that, and we find the critical points are 0, -1, and +1. So these are the critical points by using the first derivative test. Now, we could find the extrema by simply looking at values to the left and right of these points where it's equal to 0. But if we use the second derivative test, it's a little bit easier and less cumbersome. So let's see what happens next. So now we're going to take the second derivative. Remember, the first derivative ended up being 4x to the third minus 4x. The second derivative, therefore, is going to come out to be 12x squared minus 4. If we factor that, we can find the points of inflection, all right? First derivative test gave us critical points, all right? The second derivative test is going to give points of inflection. This is where it changes concavity at these points here. And so we got plus the square root of 3 over 3 and minus the square root of 3 over 3. All right, so let's create a table based on what we've got here. So I've got our critical points here, and they're going to be our test values, if you will, okay? So we got -1, 0, +1. We have our points of inflection, if you'll notice, minus the square root of 3 over 3. That basically corresponds to this point here, all right? And plus the square root of 3 over 3 corresponds to this point here. So the interval over here is going to be from minus infinity to minus the square root of 3 over 3. To the right over here is going to be plus the square root of 3 to positive infinity. And then in the middle is simply minus the square root of 3 over 3 to plus the square root of 3 over 3. So we've got three regions here that we're dealing with. And in these regions, we have three critical points. All right. So if I take, remember now, this is where the first derivative is equal to 0. So if I take the second derivative at these points, so if I take the second derivative, remember the second derivative is up here, all right? If I plug in -1, I get a positive number. We don't care what the actual value is. All we're concerned with is if it's positive or negative. Well, since that's positive, we have something which is concave up. Okay, concave up because it's the second derivative is positive. All right, our next critical point in this interval here is 0. So if I plug in 0 for x, I come out with the second derivative being negative. So this means at this point 0, or in this interval, I should say, it's concave down. And then lastly, the critical point +1, which is in this far right region, if I plug that into the second derivative, I find that it is also positive. So therefore, it's concave up in this region. Now, we wouldn't, as I said earlier, we could do this without doing the second derivative test by simply looking for whether the first derivative is positive or negative on either sides of these critical points. But I think using the second derivative test is another way of doing it. I think it's also a little bit easier, less calculations involved to do the second derivative test. So now let's look at these three regions. Notice we said for the first region it was concave up, all right? So at -1, it's a minimum. And at 0 here, it was concave down. So at 0, it's a maximum. And then lastly, at +1, it's concave up again. So it's also a minimum at +1. So now, based on this, if we were to get a rough sketch of the graph of this, it would look something like this. So it'd come down, go through here, go up through 0, and then back up like that. And so we can see, theoretically what it looks like, and then if we were to graph it, we'd see the graph would look something like this. So this is how we can use the second derivative test to find the relative extrema of various functions.